Before moving forward with our more rigorous modeling of phase equilibrium, I wanted to show you some example calculations of how you would actually go about calculating the changes in Gibbs free energy. Hopefully this will give you some practical perspective, and at the end of the video, it will hopefully motivate you to see that Gibbs free energy is actually not the most efficient way to model phase equilibrium because there's a slight problem with it. Hopefully that'll be clear by the end. But let's start with the practice problem that we have a mystery substance, so we cannot look up any data that we need in a table. So I'm not telling you what it is. Actually, I don't know what it is either. So we are setting the reference state, and we are going to say that the liquid phase at 300 Kelvin and 1 bar is the reference state. So that is where Gibbs free energy is going to equal 0. Now recall that the answers that we're going to calculate are not going to be the absolute values of Gibbs free energy, but anytime you calculate what the value of a property like Gibbs free energy or entropy or enthalpy or something, that's always going to be relative to whatever reference state you choose. So we have some other given data. We have the Gibbs free energy of the vapor phase at the same temperature and pressure. So this 5,000 bars per bar cubic centimeter per mole could also be called the molar Gibbs energy of vaporization if you wanted to, because it compares the property of the vapor phase to the liquid phase. We also have the molar volume of the liquid at the reference state as well. And we want to be able to calculate what the Gibbs free energy of the liquid and vapor phases at the same temperature but a much lower pressure are. And we also want to be able to calculate the vapor pressure of the substance at 300 K. So this is an example of how we could go about modeling what phase equilibrium is by using the Gibbs free energy. So just to organize ourselves a little bit, I did this before the video started. I like to show you how I like to put my data into Excel. I like to have the variable name on the left-hand column, the actual value numerically in the middle column, and then the units on the right-hand column, and that helps me stay organized. Another thing I like to do is name the variables from time to time, so this can make my formulas a little bit easier to type in. So I've already named this one. So if you click on the cell, you can click up here. This is the name bar. You can name your variable whatever you like. I caution you to not name the variable something like P1, because Excel will interpret that as the value in cell P1 instead of pressure 1. So that's why I said initial P here. Here I can name it final P if I wanted to, and then I'll name this one initial T. Keep it all lowercase. I keep all these lowercase, yeah. You could also name these. I'm just not going to name them for clarity, but you could name them as well. And you could go as crazy as you want to. This is just something that helps me occasionally. So this is all the given information we have. We know that T1 and T2 are the same. So I can put that in there as well. We want to calculate the Gibbs energy of the liquid at 300 K and 1 bar. So how do we go about doing that? Well, we could start with the fundamental property relationship for Gibbs free energy. We know, we've derived this before, that the change in Gibbs free energy is equal to the molar volume times the change in pressure minus molar entropy times the change in temperature. And for this particular operation, we do not have a temperature change. T1 is equal to T2. Therefore, we can get rid of this SDT term because there is no change in temperature. So simply, we're down to the change in Gibbs free energy is equal to molar volume times the change in pressure. So we have to calculate this a little bit differently depending on which phase we have. So let's start with the liquid. That one's a little bit easier. If I had an equation of state that would relate the vapor to the pressure, so if I knew that this mystery substance was well modeled by the van der Waals equation or the Pang-Robinson equation of state or the Suave-Redlich-Kwong equation of state, I would plug in the value of V in terms of P, and I would integrate and solve from there. However, I want to keep this discussion general and not assume a particular equation of state right now, and this problem is just for illustrative purposes anyway. So I'm going to assume that we have an incompressible mystery substance. In other words, if I change pressure, the volume will stay the same. I can rationalize that by going back to my P versus V plot that I did a couple of videos ago. And remember that the liquid phase was represented by this relatively vertical line. So if I zoomed in a lot, you would still see that it's vertical, indicating that as pressure is changing greatly, so pressure can change by 300 bar, and molar volume would barely change at all. So that tells you that for a liquid, it's a reasonable assumption to make that V underbar does not change as a function of pressure. So if we treat it as constant, that will allow us to pull it out of the integral and then integrate that expression. And I've done this previously as well. So again, pulling it out of the integral, and then I can integrate dg from Gibbs energy 1 to Gibbs energy 2, and p from p1 to p2. Those are both just integrals of a constant, so I'm left with this equation when I plug in my limits of integration. Now I know what G1 is, I know what molar volume of the liquid is, and I know P1 and P2. So this is a simple equation that I can solve for G2. So over here in my calculation box, I am going to do that formula. So I'm going to say that this cell is equal to G1. I have to move over to the other side, but remember I have Gibbs free energy of the liquid, so that's going to be 0 plus V underbar times the change in pressure. So it's P2 minus P1, so I can use my variable names here. So final P, notice how it picked up what cell I want to reference here, minus initial P. And that would give me what the Gibbs free energy of the liquid is. Minus 123.75. The units here should be the same as Gibbs free energy because my units have to be consistent if I'm using this formula. I just quickly double check if I multiply bar times V under bar, I'm left with the same units of Gibbs free energy. So that works out. Okay, fine, that is easy enough to calculate the Gibbs free energy of the liquid. What about Gibbs free energy of the vapor? So I got to go back to my original equation, say dg is equal to V underbar dp. I cannot assume that V underbar is constant for a change in pressure, especially for a vapor now. So what do? I have to assume an equation of state here, and to keep things simple, and also with the knowledge that I'm lowering the pressure, I'm not increasing the pressure. So I have relatively low pressures. The highest pressure I have in the problem is 1 bar. So I'm going to go ahead and assume ideal here. That may be a little bit off, but hopefully good for illustration purposes in this problem. So for this one now, I have to not pull V underbar out of the integral, but I have to express V underbar in terms of P such that I can integrate it. So by the ideal gas law, V is equal to RT over P. And when I integrate this expression now, I get this ln of P2 over P1 term. But another relatively simple-ish equation where I can just plug it in basically and see what I get. I'm also going to need the value of the gas constant at the consistent unit. So I'm going to look that up quickly. All right, I had to go look it up real quick, but a value of 83.14 bar centimeters cubed per mole Kelvin should be consistent in the units we have. I'm going to go ahead and name that variable R. I'm going to see if that accepts that as a name. Let's see, maybe it won't. So R, enter. Yeah, it's not letting me say it's, not letting me name that value. That's okay. We'll just reference the cell if we need it. And we will need it. So it is going to be G1, which is not 0 in this case, but is the Gibbs free energy of the vapor because we're modeling the vapor phase now. So Gibbs free energy of the vapor plus R times T times ln of P2 divided by P1. And notice I can just click the cell and it'll input my name of the variable for me. This is also good for when you're troubleshooting and you want to make sure that your formula is correct. If you name your variables, it'll be a lot more familiar to you than looking at Excel cell names. Okay, wow, that is a very largely negative Gibbs free energy of the vapor phase. So let's evaluate, see whether or not it makes sense. At a very low pressure, what should we expect the phase of this substance to be? For any substance, if we decrease the pressure, we should be getting a vapor phase. So remember that I can evaluate or predict which phase any substance would be by calculating what the Gibbs energy of both phases are, and then the one with the lower value will be what phase I expect to see. So because negative 110,000 or so is much less than minus 123, we definitely assume, or we presume, or predict that we'll have a vapor phase for this substance at this temperature and pressure. Now, for the original temperature and pressure for 300K in 1 bar, notice that my Gibbs free energy of the liquid was 0 and my Gibbs free energy of the vapor was positive. It was 5,000. That tells me that at my initial temperature and pressure, the Gibbs free energy of the liquid was lower, and therefore I have a liquid at that temperature and pressure. So an interesting question would be then, well, at what temperature and pressure are the Gibbs free energies equal? And that gets at our second problem of calculating what the vapor pressure of the substance is at 300K. In other words, at what pressure will I have equal Gibbs free energies? So in order to do that, I'm going to set up another cell. And I did not $sign these values appropriately. So I'm going to need to either do it another time or, yeah, I think I'm just going to type them in again. So for this, I'm going to use GoalSeek. I could use Solver for this one. However, I think GoalSeek could be a little bit simpler. And if you can ever use GoalSeek, I prefer to use GoalSeek just because it's easier and more difficult to mess something up. But remember, the criteria here for phase equilibrium is that the Gibbs free energy of the liquid and the vapor phases are going to be equivalent. So I'm going to take my formulas. Remember, this is my formula for the Gibbs free energy of the liquid. So G2 of the liquid is equal to this one. Gibbs free energy for the vapor is equal to this one. So I'm going to put these things on both sides of the equation. Maybe I'll pause and write that out so it's clear what I'm doing. Hold on. Okay, I've got things arranged neatly how I want them. Again, I'm starting with the equilibrium criteria because that's what vapor pressure is at a certain temperature that's analogous to the boiling point at a certain pressure. I've got equal Gibbs free energies. So I'm going to plug in my expression for Gibbs free energy of the liquid, which just putting G1 over to the other side is this formula transcribed there. And same thing for the Gibbs free energy of the vapor is transcribed there. So if I put these on both sides, so I'm going to solve this equation for 0. Now I'm going to type this thing into Excel and GoalSeek it to be 0. I like to GoalSeek things to be 0 because, again, that is a way that I can minimize my mistakes. So I'm going to say this formula is Gibbs energy of the liquid. So this cell plus the molar volume times P2 minus P1 minus Gibbs energy of the vapor plus, nope, I missed a negative sign there. This should be negative as well. So sorry about that. I snipped that as a picture, so I'm not going to change it. This should be a negative right there. Negative R times T times ln of P2 divided by P1. Okay, now obviously my P2 is not correct here because I'm getting an answer that is non-zero. So I'm going to use GoalSeek. So that's again data, what if analysis, GoalSeek. And this is a much easier and simpler input bar. I want to set cell of B20 equal to value 0 by changing the value of the cell P2. I want to find the P2 that makes this equation true because that's my saturation pressure. And Solver is going to chug and, oh, that doesn't seem correct. I think I made a mistake. Oh, I'm sorry, that actually makes perfect sense. I want my GoalSeek to be 0. Something times 10 to the negative 7 obviously is very small. What I want to look at here is what my GoalSeek cell is. So it tells me that at a pressure of 0.8176 bar, I will have phase equilibrium, which makes sense, right? That is a number that is between 0.1, which I already described that that's how we know it's a vapor, and 1, which we know is a liquid. But here's a problem with this. So this problem is solved. I want to point out an issue here that look at the degree of precision that we have. If we were to round this value, so let's say we round it to 0.818, for example. Now let's see what value we get. Now we get, for a difference in the Gibbs free energy, we get 12, right? So we didn't really change this value all that much. We just rounded it to the third significant digit, which is typically pretty acceptable, right? But if we evaluate that, it looks like our answer doesn't really make sense. And if we round it even further, right, we get an answer that looks even further from the truth. So the problem with using Gibbs free energy is that it's very, very sensitive to very minor changes in pressure. And to investigate why that is, let's do a more general calculation. This is why I love Excel so much, because you can do the same calculation over and over again, and you can do plots, and it makes it way easier to see. So let's make a column for P2 here. And now for many different P2s, we can evaluate what the answers that we get are. So let's start at P1. P2 is equal to 0.01. And we've already done 0.01. Let's start at 0.05. And let's increase by increments of 0.05 until we get back to a pressure of 1. So this will enable us to get a good sense of our data. So I'm going to do a little bit more. All right, that'll be good. In this column now, I'm going to zoom out a little bit so we can see the whole thing. In this column, I'm going to put the formula for Gibbs energy of the liquid. And in this formula, in this column, I'm going to do Gibbs energy of the vapor. All right, I'm going to pause and let you practice this. Actually, in the interest of transparency, I'm going to show you exactly what I'm doing. I'm going to copy this formula down. So I want to $ everything. I think variable names, I think, are always absolute referenced, by the way. So I'm going to copy and paste this formula. And I'm going to double check that it took the values that I wanted it to, and it did. The only thing I have to change is that instead of final pressure, I want it to change this formula to be the value of P2. So here I want cell A26 instead of final pressure. All right, and that should give me an answer that is the same as if I plug in 0.05 there. Yeah, I get the same answer, 118.75. So that tells me that my equation is correct. Now, because I $ everything else, I should be able to just copy this all the way down. This tells me what my Gibbs energy of my liquid is. I'm not liking that value. Oh, that's a times 10 to the minus 14. That minus snuck in. So that tells me it's approximately 0, which again makes sense, right? Because that is our reference state. Liquid phase, 1 bar. This is all for 300 Kelvin. So this is P2 in bar. All right, same thing for Gibbs energy of the liquid. I want to $ everything that I can. So I'm just hitting F4. And I don't have to $ my named variables. I want to copy this formula down to GV. And I want to substitute final pressure. I don't want final pressure. I want cell A26 again. Okay, copy that all the way down. And now I can do a cell or a column where I say Gibbs free energy of the vapor minus Gibbs free energy of the liquid. And by doing this calculation, this will tell me if I should have a vapor phase present or a liquid phase present. So if this number is positive, that tells me that Gibbs energy of the vapor is greater, and I'll have the liquid phase. If this value is negative, it tells me the opposite. So I'm going to say equals vapor minus liquid. And if I want to get really fancy with my Excel statement, I can do a formula bar where I say if this value is positive, like I said. So if it's greater than 0, I want it to output that my phase is a vapor. Wait a minute. So if it's positive, vapor is going to be greater, and I'm going to have a liquid. And then my value, if false, is vapor. Okay, so I have vapor phase, and this should tell me, again, that at my somewhere between 0.8 and 0.85 is where I shift from vapor to liquid phases. All right, so this is another interesting, cool thing that you can do with Excel. I'm just showing you tips and tricks at this point. But what I want to do is plot both of these as functions of P. So I'm going to insert a chart here. And let's see, this looks backwards to me. I want that plot. Yeah, I think I've plotted it the opposite way. So I want pressure on my, what do I want? I want pressure on my x-axis and Gibbs energy on my y-axis. Is that what I have? I have Gibbs, no, this is, I had it right in the beginning. So I want Gibbs, there we go. Okay, that's what I want, right? Gibbs energy is on my y-axis. And it tells me again that at a pressure of 1, my Gibbs free energy is 0. All right, so I want to superimpose now on this plot by itself doesn't really tell us much. What I want to do is say select data and add a data series. I want to superimpose the data for the Gibbs energy of the vapor on the same plot. So I'm going to highlight my pressures. That's going to be my x-axis again. My y-axis this time is going to be vapor. Now look at the difference. So the orange is my Gibbs energy of the vapor, and as I go to zero pressure, I should be blowing up to negative infinity, right? Because as P2 gets smaller and smaller, this ln value should go to negative infinity, right? ln of 0 is negative infinity. So what am I illustrating here? I want to show you that as pressure is changing, that's our x-axis, as pressure is changing, the liquid Gibbs energy barely changes at all, whereas the Gibbs energy of the vapor is very sensitive to small changes in pressure. So let's zoom in on this plot, and I'll show you that even clearer. Let's zoom in from the area of 0.8 to 0.85, and we'll see what it looks like. Oh, that's not going to be instructive. I want to zoom in on the y-axis as well. Let's just go from negative, let's see, I don't know, 150 to positive 150. Let's see what it looks like. All right, see, look at this. Our intersection point, again, right there, this is 0.8176, blah, 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 or whatever. If I change that just by a little bit, notice how different these slopes are. So that's the problem with using Gibbs free energy. It's very, very sensitive to changes in pressure for the vapor phase, not so sensitive to changes in pressure for the liquid phase. And that is the motivation behind defining another thermodynamic property known as fugacity. And that'll be the subject of our next video.